In this video, I'm going to discuss some of the topics related to complex numbers. So many of these examples and the information contained in this video can be found in the OpenStax College Algebra textbook. I've included the link at the bottom of each of these pages. So complex numbers, first of all, you need to know that standard form is a plus bi, where a is the real part and b is the imaginary part. I is defined as the square root of -1. So that's some information that we'll come back to throughout the section. So in previous examples and previous sections, whenever we've had square roots of a negative number, we just said it's not a real number and we moved on. But now we know that it is actually a complex number. It's not a real number, that's true, but we're going to learn how to deal with these and reduce them so that we can manipulate them in different ways. So what you have to realize is this is the same as the square root of -1 times 36. The square root of -1 is I. That's what it's defined to be up here. And the square root of 36 is 6. So this -1 comes out as an I. It comes out of the radical. And the square root of 36 is 6. That comes out of the radical. So 6i would be the answer here. You're going to reduce these just like you would, or simplify these just like you would if there wasn't a negative. You're just adding the I at the end. So the square root of 36 is 6. The square root of -36 is 6i. So that negative comes out as the I. So in example 2, the negative will end up being an I. The 50 is not a perfect square. So what we're going to do is we're going to do a prime factor tree and see how we can reduce this. So I can break this up into 5 times 10. 10 will break up into 5 times 2. 5 and 2 are both prime. So now what I'm looking at is the pairs and the singles. So remember, the pairs come out and the singles stay under the radical. So the negative comes out as an I. The pair of 5s comes out as a 5. So that will be 5i, and the 2 stays under the radical. So that would be the simplified version of the square root of -50. So from this point forward, we expect you to know how to simplify a radical with a negative under the radicand. You cannot simply say not a real number anymore and move forward. You need to simplify it and use the complex number system. For number 3, the negative should jump out at you. That's going to come out as an I. And then what we want to do is try to make a prime factor tree for 1,440. So again, you can break this up in any way you'd like. I notice that it ends in a 0, so I'm going to divide by 10. So 10 and 144. 10 breaks down into 2 and 5. 144 is 12 and 12. Okay. Now, even though these are not 12 and 12 are not prime, but notice that I have a pair. If I wanted to, I could stop there and know that the pairs come out. So these 12s are going to come out. This will make my work less. Now, if I wanted to go ahead and break down the 12s like I always do, I can. You're going to have more pairs to take out. Okay? So if I stopped here, a 12 would come out. A 2 and a 5 would stay under. So that stays under and that stays under. So this would become 12. The negative comes out as an I times the square root of a 2 and a 5 are left under. So you multiply those back together. So you get 12i square root of 10. All right. Now I want to go ahead and work it out and pretend like I didn't see the pair of 12s. So let's say I had 1440 and I did 10 and 144. And I did 2 and 5, and 12 and 12, 3 and 4, 3 and 4, and then the 4s are 2 and 2, 2 and 2. Okay, so let's just say I'm just going through it. I don't notice the 12s. What I want to do is I want to look for pairs, right? So I have a pair of 2s here. a pair of 2's here. I have a pair of 3's here. Kind of awkward because they're not next to each other. And then I have this leftover 2 and the leftover 5. So the pair of 3's comes out as a 3. The pair of 2's comes out as a 2. The other pair of 2's comes out as a 2. So 3 times 2 times 2 is 12. So I get the same thing either way, right? And then the 2 and the 5 are single, so those stay under. So I would still get 12i square root 10. Okay, I just want to show you both ways. So if you notice a pair earlier, you can take the pair out. But if you don't, that's fine. Keep going until you get all your primes. Just make sure you circle all of your pairs. All right, number 4. Perform the indicated operation and express the result as a simplified complex number in standard form. So, notice that we have 2 complex numbers here. They're denoted with parentheses. So in the first, right, in this first one, this is one complex number, and this is a second complex number, right? In the first complex number, I have the real part and the imaginary part. And in the second complex number, I have the real part and the imaginary part. Remember that the standard form is a plus bi, where a is the real part and b is the imaginary part. What you're going to do is you're going to get rid of the parentheses by doing distribution if necessary. And then you're just going to add your like terms. The real terms are like, you'll add those together. And the imaginary parts are like, you'll add those together. So in this example, you have an addition sign. Your parentheses really are not necessary. So if you drop the parentheses, you have negative 2 minus 4i plus 1 plus 6i. You're going to combine your like terms. So you've got the real parts, right? The real parts are in yellow. So you'll add those together. So negative 2 plus 1 is negative 1. Okay. And then the imaginary parts, let's see, let's do that in red. So the imaginary parts are negative 4 and positive 6. And you know that's the imaginary part because they're connected to the I, right? So negative 4i plus 6i is plus 2i. So that is your answer. That's the sum of the 2 complex numbers given. Here is something important to know. If you put your answer as 2i minus 1, that is equivalent, but that would be wrong because it's not in the standard form. The I has to go last. You have to put the real part first and the imaginary part second, or it will be counted wrong. So make sure you put in negative 1 plus 2i and not 2i minus 1, okay? It might not tell you that explicitly, but that's always going to be the case. You should always write it in standard form. Even if it doesn't tell you that, you're expected to know to do that. Okay. So now we're going to look at a few more. Same idea. We're going to perform the indicated operation, write it in standard form. So number 5 is a subtraction problem. So we're going to subtract one complex number from another. The key here is we're going to distribute that negative before we just drop the parentheses. So it will be 2 minus 3i, and then we'll have minus 3 minus 2i after distributing that negative. And now we're simply going to combine our real parts and imaginary parts. So 2 minus 3 is going to be negative 1. Negative 3i minus 2i is negative 5i. So that will be the complex number we get when we subtract the 2 complex numbers given in standard form. All right, number 6. This is a product. So we're multiplying 4i times 2 plus 3i. This is just the distribution property. So 2 times 4i is going to be 8i. 3i times 4i is going to be 12i squared. Remember that I times I is I squared. Now here's something important. I squared is equal to -1. Okay, so write this down in your notes, highlight it. You should remember this. This is very important. Anytime you see an I squared, you're going to have to reduce it. In fact, you should never have an exponent on an I. That's never considered simplified. You cannot have an exponent on an I. If you do, then you need to simplify it. So in this case, we need to realize that I squared is equal to -1. So that means we're going to multiply 12 times -1. So we'll have 8i. 12 times -1 is -12. Okay, so now we've gotten rid of the exponent on the I. And now the last step is making sure we write it in standard form. So the real part has to go first. So -12 is the real part. 8 is the imaginary part. So it has to be written -12 plus 8i. If you leave it like we did in that last step, the 8i minus 12, that would be incorrect. So make sure you rewrite it in standard form. All right, the next one, we have another product. So we're simply multiplying the 5 times the 6 minus 2i. So if we distribute, we're going to get 30 minus 10i. Nothing else to do here, so that's done. Notice the difference between number 6 and number 7. In number 6, we were multiplying by another I, but in number 7, we were multiplying by 5. So that's the difference, right? Number 8, again, we have a product, but this time we have two complex numbers that have two terms, right? A real and imaginary part for both. All we're going to do here is use the distributive property like we would if I was a variable, okay? So 2 times 4 is 8. 2 times -i is -2i. 3i times 4 is plus 12i. 3i times -i is -3i squared. All right, so let's look over what we have. First thing we notice is this I squared. We cannot have an exponent on an I, so I'm going to cancel that out and make it a -1 instead, because I squared equals -1. And then another thing I notice is that I have like terms. So I'm going to combine those. All right, so I have 8. The -2i plus 12i is going to be 10i. And then -3 times -1 is going to be +3. Now I can see that I have like terms again. I have two real parts, so I'm going to combine those. And 8 plus 3 is 11. Bring down the 10i. I have the I last. So here is my answer. So very similar to working with variables, right? Difference is if you have a power on an I, you have to simplify it. All right, so let's look at this next one. We need to distribute. So 4 times 4 is 16. 4 times 2i is 8i. -2i times 4 is -8i. And -2i times +2i is -4i squared. So again, let's look for things that we need to be watching out for. I to an exponent. I need to simplify that. I squared is -1. Like terms. Here they are. Do you notice anything about these like terms? Notice that they're opposites, right? I have a +8i and a -8i. Those are going to zero out, so those are going to cancel out and be gone. So let's see what we have. We now have 16. -4 times -1 is +4, so +4. 16 plus 4 is 20. So we just have an integer, right? A whole number. Anytime you are multiplying complex conjugates, that means they have the same numbers but a different middle sign. So that means you have a plus bi times a minus bi. That's always going to get rid of all of your imaginary parts, and you're going to be left with a real number every time. So complex conjugates, and we'll see the importance of this in just a couple examples ahead. All right. So now if we have a complex number squared, remember that this really means 9 minus 7i times 9 minus 7i. So it's the same thing multiplied together twice, right? Don't try to distribute the exponent because that's not a valid operation. So we're going to distribute it all the way out. So 9 times 9 is 81. 9 times negative 7i is negative 63i. Negative 7i times 9 is negative 63i. And negative 7i times negative 7i is plus 49i squared. All right, so let's look for the things that stand out. Number 1, I to a power. We know that I squared is negative 1. And then we're looking for like terms. So the like terms are in the middle here. Those are both the imaginary parts. Now, don't make the mistake of canceling those. Those do not cancel out because they're the same sign. Remember, they cancel if they're opposite signs. So we need to bring those down. So we'll have 81. The two negative 63i's will combine to be negative 126i. And then 49 times negative 1 is negative 49. And so now we want to subtract. So the 81 minus the 49, when we do that, we get 32. So 32 minus 126i. Okay. Now 11 and 12, these are going to work totally different. So look at the difference. Number 11, the denominator is a 2. Number 12, the denominator is a 2i. So here is the difference. If you remember from chapter 1 in one of the prerequisite sections, we talked about rationalizing the denominator, that we could not leave a square root in the denominator of a fraction. So remember that an I stands for a square root, right? I is the square root of negative 1. So we cannot leave an I in the denominator. That's going to be the case for number 12. Okay, so let's go back and look at number 11. I just wanted to point that out, the difference. Okay, so number 11, all we're doing here is trying to break up this into two pieces, the real and the imaginary parts. So the real part is 3 over 2, plus the imaginary part is 4 over 2i. So 4 over 2 is 2, and then you have the I. That's all you're doing for number 11. All you're doing is splitting it up into the real and the imaginary parts. Okay, that's it. Number 12 is totally different. Number 12, you're trying to get rid of the I in the denominator. Whenever you have one, like a monomial, like just one thing with an I, you're going to simply multiply the top and the bottom by I. So in the top, you're going to distribute the I. On the bottom, you're just going to multiply. So you've got negative 5i plus 3i squared over 2i squared. All right, so now you're looking for all the things that you're supposed to look for. Do you have any i's to exponents? Yes, you've got to reduce those. So I squared is negative 1. Everywhere you see an I squared, you're changing it to negative 1. So we're going to take care of that first. So we have negative 5i, 3 times negative 1 is negative 3, over 2 times negative 1 is negative 2. Okay, so now we are in a situation where it looks like number 11. Now we just have a regular number, an integer on the bottom, no I. So now you're trying to split it up into real and imaginary parts. So first, let's rewrite the top in the correct order. So negative 3 minus 5i over negative 2. And now we're going to divide. So we have negative 3 over negative 2. So the real part is 3 halves because the two negatives make a positive. And the imaginary part will also be positive 5 over 2 with the I. So there is our complex number written in standard form. So the first part is getting rid of the I in the denominator, and then you're splitting it up into real and imaginary parts. Okay, so number 13, notice the difference here. You don't just have 2i or 3i. You have a full complex number with a real and imaginary part. It's 4 plus 3i. In this case, you have to use the complex conjugate every time. So if you have a full complex number that has a real and imaginary part, you're going to always multiply by the complex conjugate of the denominator. So that'll be 4 minus 3i. So the same two numbers, different middle sign. 4 minus 3i. Remember that whatever you do to the bottom, you have to do to the top. All right, so if you need to write in parentheses to remind yourself you're going to distribute, you should do that. So we're going to distribute on the top and the bottom. So 2 times 4 is 8. 2 times negative 3i is negative 6i. Negative 3i times 4 is negative 12i. Negative 3i times negative 3i is plus 9i squared. So that's the numerator. The denominator, we have 4 times 4 is 16. 4 times negative 3i is negative 12i. 3i times 4 is plus 12i. 3i times negative 3i is negative 9i squared. All right, so let's look. I squares. Those have to change into negative ones. Okay. We're also looking for like terms. So on the top, on the top we have negative 6i and negative 12i. On the bottom we have negative 12i and positive 12i. Look at the bottom. Those are opposites. Those are going to cancel out. And you should expect that because the denominators we multiplied complex conjugates. The whole reason we did that is to get rid of the I on the bottom. When you're doing these, if all of your i's do not go away on the bottom, then you did something wrong. That should happen. That's the point of this, okay? So 8, negative 6i minus 12i is negative 18i. 9 times a negative 1 is negative 9. And on the bottom we have 16. Negative 9 times negative 1 is plus 9. So now we're going to combine our like terms. On the top we have 2 real parts, and on the bottom we have 2 real parts. So 8 minus 9 is negative 1 minus 18i over 16 plus 9 is 25. And so now our last step is just to separate it into real and imaginary parts. So you have negative 1 over 25 is the real part, and negative 18 over 25 is the imaginary part. So negative 1/25 minus 18/25 I. All right, so that shows you how to add, subtract, multiply, and divide complex numbers. And the last part of this section that I want to look at are powers of I. So if you look at this chart, it shows you that there is a pattern that repeats. So I is equal to I squared is equal to negative 1, I cubed is negative I to the 4th is 1, and then it starts over. I to the 5th is I to the 6th is negative 1, etc. Okay, so this pattern repeats over and over and over, okay? So if you have powers of 4, right? So to the 4th, to the 8th, to the 12th, the next one would be the 16. So if your number is evenly divisible by 4, it's just going to be a 1. So that is what I usually try to look for. So what I want to do is break my number down into something divisible by 4. So this I to the 33rd, remember your exponent rules. You can break this down into I of 32 plus 1, right? We agree that 33 is the same as 32 plus 1. And when I'm doing that, I could rewrite that as I to the 32nd times I to the 1st. That's equivalent to I to the 33rd. The reason I wanted to break it down like that is because 32 is evenly divisible by 4. If the exponent is evenly divisible by 4, then that piece is going to simply be a 1. 1. So now I have 1 times I to the 1st, which is just I, and 1 times I is I. So now I'm done. Remember I said earlier in this section that you never want to have an exponent on I. You always have to simplify it. So that's what I'm doing here. Okay, so simplify it until you have an I, a negative I, a 1, or a negative 1. So if I look at number 15, 52 itself is evenly divisible by 4. So that means that this is just going to be 1. So my answer is 1.